All right, let's get started. So, welcome back. This is lecture 4 for Machine Learning 2 class, DS 4420. This is Professor Wu. So, let's get started. We previously talked about supervised learning, right? Basically, we started off with some data as well as some label. And the idea is that you want to find a function, f, such that when you put the data in, your prediction is approximately, well, as close to the label as possible. Right? So this is based the fundamental idea of supervised learning, is that you're trying to make some kind of prediction, and you want to learn the function such that your prediction is does a good job, right? And we learned last time the concept of regression. That's one way to essentially train the function, is that we want to find a function such that when you put the data in, your prediction is, and the actual truth, you want their difference to be as small as possible, right? So this is your prediction output. This is what's actually truth. Therefore, the difference between them is the error. And what you want is you have n samples. Therefore, when you average all the error together, that would be the average error. So, well, we actually average the error square. So when we average the error, this right here is the average error square. If you're able to find a function that makes the average error as small as possible, then you found essentially the best possible function you can find. And we mentioned finding this function is not easy because, well, there are infinite functions. How are you going to find the best one? So, what we normally do is that we make assumptions of basis functions, which means that we don't know what the function is, but we can say that maybe it's a combination of bunch of functions. So you say this is one function, another function, another function. So you make up a bunch of functions, and then you just assume that your final function is the combination of them. The weights here, we don't know. Like we would like to find the weights such that we get the right proportion of these functions. Okay. So once again, we know we pick the functions ahead of time. We find the weights to essentially guide us towards the optimal function. So given what we learned from linear algebra, we can split this into this and this, okay, which is then written as W transpose phi. So this right here is W transpose, and this right here, we're gonna which has m number of basis functions. Instead of writing m of them every single time, it'll be easier for us just to write phi. So, so this is where we left off last time. Now, once we have assumed that this is how we're going to construct a function, what is rest is basically based on how we pick the basis. Depending on how we pick the basis, then we can get different type of functions. There's two type of bases that is most commonly used and the easiest. The first one is called linear regression. You only pick two bases, phi 1 and phi 2. That's it, right? And phi 1 is equal to x, phi 2 is equal to 1. Therefore, you're saying that your function essentially looks something like this, where this is phi 1 and this is phi 2. Now, the second one is called the second order polynomial. In that case, what you do is you pick x squared as phi 1, and then x is phi 2, and 1 is phi 3. So your function will look something like this. So notice here, there are three bases. Therefore, you need to know the weight for all three of them. Over here, only have two. It only has two bases, so you only need to know two weights. The weights are important because they tell you how these combination functions combine to form your ultimate final function. Now, there are two ways to solve like regression, right? One is the gradient descent, which is what we did last class, gradient descent. And the second one is closed form solution. The gradient descent method is you have some kind of function you're trying to minimize, right? This was the mean square error. You're trying to minimize the mean square error, okay? And then when you try to minimize it, you minimize it by finding the W. To find the W that makes this as small as possible, we use gradient descent. We learned from last class how the gradient descent algorithm works. It works by calculating the next W with the existing W with this update. Now, the gradient tells us which way to go. If you remember, if you're trying to find the minimum, which is right here, the gradient tells you that this goes down, this goes down, this goes down until you reach this point. That's why if you have some kind of starting point, W0 as the starting point, every time you run this update, you're going to get a little bit closer. Okay? So the gradient descent is an incremental algorithm that lets you slowly get towards the optimal solution. And this works for basically like any function. So gradient descent is the standard, because very often this is the only way you can solve a problem. However, for the problem of regression, like linear regression or the type of regression we're working on, a closed form solution also exists, which means that what you can do is that you can simply calculate the derivative of this and set it to zero, and that's all you have to do. When you set it to zero and calculate for W, then you have the solution. That's much easier than running the entire gradient descent algorithm, right? um, so so once again, if you can set the derivative to zero, that's called a closed form solution. That's great, right? Then you can just solve for W and you got the solution. However, if you can't do that, then you got to do gradient descent. Gradient descent is the method that always works. So that's why I taught you that first. Closed form solution is the second way. Okay. Now, like I said, the closed form solution is when you calculate the derivative and set the derivative to zero. Now, from the last class, we know that the derivative is equal to this. This looks really complicated. How are we going to solve for W, right? Can we actually do it? And the answer is yes. Yes, we can actually do it. And it's actually quite easy if you can use some linear algebra tricks. Luckily, Professor Wu taught you how to do linear algebra in the past couple classes. So we're going to see how we can accomplish this. Okay. So, once again, I keep repeating this. It's very important for you to understand this because throughout the entire semester, you're just going to see this over and over again. All right. Now we let the function equals a linear combination functions, and then we let we split them into the matrix format, a vector format, and then we can rewrite them compactly this way. Now V transpose U is equal to U transpose V. You can flip the dot product for vectors. Okay, so you can flip the dot product. So over here, W transpose 5 is the same as 5 transpose W. Okay, so hopefully you follow along the logic here. Now, if you understand this logic, now if we want to represent our prediction, right? Let's say we have n samples consisting of x1, x2, x3, all the way to xn. Then we can represent all of our predictions, right? This our function is f. So if we put x1 into the function, that will be the prediction given x1. x2 into the function, that would be the prediction given x2, right? So you can just put every single sample here, right? So this vector consists of the result of every single sample. Now, what is f1? Well, that's just the function f, and you plug x1 in here, right? So the function f is this, so you plug x1 in here, and you plug x2 here, and then you plug x3 here, right? So this right here is the prediction for every sample. Over here is also the prediction for every sample, just written out. Well, you can, all the W's are the same, so you can just pull the W out. So it's W times every single one of them. And I'm gonna call this capital Phi, capital Phi. So capital Phi is essentially when you pass the each sample into the feature map. Each sample into the feature map. Right? So capital Phi is the result of you go from x, you pass it through the function phi, x1, then you got phi of x1, right? Then x2, then phi of x2. So essentially do that for every single sample, and you stack the results. So that is what phi, the capital Phi matrix is. Okay? So right here, the key takeaway right now is that if we want every one of our prediction, we can simply denote it as capital Phi W. So it's the key takeaway is for you to realize that we can denote passing the data into the feature map and denote that as capital Phi, capital Phi. So this is the key you want to remember. Like, you want to know what this means. If you don't know what this means, pause the video, go over this logic again, because you're not going to understand the next slide. Like, the next slide, it's all hinges on the fact that you know what this thing is. Okay, so pause the video if you don't really understand what this is or how you calculate it. Okay, now that we went through that, we are now given this. So this is the objective, right? This is the objective, and we want to calculate the derivative. If we want to calculate derivative, it is simply this. So we did this several times in the last class. Like 2 goes down. Well, actually, I think there was an n here. So 2 goes down, but it doesn't matter. Whether there's an n or not. So so this should look very, very similar. I think the other one may have 2 over n. But the constant at the front in the end doesn't really matter. Now, this is the derivative that you used last class. And this is the derivative that we use for gradient descent, right? Now let's think about this symbol, this summation symbol. What does that really mean? Well, we plug the I all the way to n samples. So what that's saying is you pick x1, you plug it in. Then you pick x2, you plug it in. You pick x3, you plug it in, so on and so forth, right? So, and you are adding them together. When you plug x1, when you plug x2, right? So you're adding every one of this together. That's what this means. That's what the sum is telling us. Now, we're going to do a variable switch just to make it look a little bit more compact. Now, when you multiply the dot product, that's going to be a number. So it's a scalar number, not vector. Y1 is the label for the first sample. So that's also a scalar. So this right here is just a number. This is not a vector. Whereas this here is a vector. So this is a vector. And this is a number. Now, we're going to we're going to call this AI. Okay, so this is AI is equal to this thing here. Okay, which is also equal to this. They're exactly the same. Well, once we simplify this notation and just call this whole thing AI, this can then be written in this form, right? Notice how this is phi 1 times A1, phi 2 times A2, phi 3. So notice it's phi 1 times A1. What is A1? It's this entire thing. So I'm basically copying this to here, except making these called A1, A2. All right, once we have it in this form, we can once again convert them. We can pull all the A1, all the constants out. When we pull all the constants out, remember, if we perform this dot product, I can simply multiply this down, this, and this, and it will once again equal to this. So I'm converting this into like a vector, into a vector format. Okay. Now this right here is a vector. That's a vector. That's a vector. So remember, these are vectors. That's a vector. That's a vector. And these are scalars. These are just numbers. Okay. All right. So after this, let's substitute A back. What was A? A was this, which is also the same as this. So let's just copy it back. A1 is equal to this thing, right? Look, A1. And then A2 is equal to this thing. Okay. So A3, A4, so on and so forth. Once I have this copy back, then wait a second, W's are here, so we can just pull the W out. So now W multiplied by this entire thing, subtract by Y1. So I just rewrote this entire thing once again. After I rewrote this, we can take a look. What was the takeaway from last page? All right, let's look again. I keep saying you have to understand what this is. Okay? Guess what? This is identical to this. So we can now really, really simplify it. This right here is simply phi. This is W, and we're going to call this entire thing just Y. Okay? And this is the transpose of this. Therefore, this is phi transpose. Therefore, we can calculate phi transpose phi W minus Y. So this entire thing is equivalent to this. Now, over here is you have to use a loop to essentially calculate the derivative. Over here, there are a bunch of matrices, and you just multiply them together. This is much easier to calculate. Or you rather be doing a bunch of matrix multiplication than doing a loop and summation. Okay, so this right here is the derivative, is equivalent. It's equivalent to this. Okay, they're equivalent. And over here, we basically showed you all the steps of why they're equivalent. It's essentially a conversion from a summation format into matrix format. Okay? So we just spent all this time to essentially learn how to rewrite the derivative in the matrix vector format, right? Why is that? It's because once we have it in this simple format, it is really easy to set this to 0 and solve for W. Okay, we can set this to 0. See, here's the derivative with respect to W. We set it to 0. Okay, well, now after we set it to 0, I can distribute this, right? So this times this and this times this. And we want to solve for W, right? So when we solve for W, we move this to the other side. And we move this to the other side, which is right here. I skip a step. I wish I did not skip a step. So after I move it to the other side, you see how I got this, right? So I move this to the other side. After this, you can just multiply by the inverse of this. Phi transpose, phi inverse. All right? And you can do that on the left side. You want to multiply the inverse on both sides. So phi transpose phi inverse. So this times its inverse cancels each other out. Therefore, the solution is simply W is equal to phi transpose phi inverse phi transpose Y, which is what I have written here. Now, this is the solution. You don't have you if you know the phi matrix, you know your labels, you simply multiply them together and you get the solution. And this right here is the closed form solution. Okay? Now, how do we find this inverse? Well, for a small matrix that's just 2 by 2, right? So, let's say the 2 by 2 numbers are A, B, C, D. To find the inverse of this, it's AD minus BC, right? And then multiply this number by flipping the A and converting BC to negative. So this right here is how you find the inverse. So if we calculate phi, right? If we know what phi is, we can do matrix multiplication phi transpose phi. Then we can use this equation to find the inverse. After we find the inverse, we then multiply matrix multiplication by phi transpose and y. Then voila, there is our optimal solution. Okay. Now let's take a closer look at what phi is. This phi matrix. I really, really emphasize on phi because this is something we will do over and over again throughout the entire semester. So if you don't understand it, like it will be very hard later. Now, what was phi? Okay, remember that phi was, well, phi x1, phi x2, phi x3, right? You're essentially passing each sample through the feature map. And remember that when you have put a sample inside a feature map, you're putting that sample through each basis function. So there are multiple basis functions. So when you put a sample inside a basis function, this gives you a scalar. This gives you a scalar. Therefore, the feature map, gives you a vector. So we then stack this vector for every single sample. Okay? I know I'm repeating myself, but this is the part that if you don't get, then nothing else makes sense. Now, with linear regression, remember I told you we only need two basis functions. We only need two of them, phi1 and phi2. Phi1 is just x, phi2 is equal to 1. So with this, the capital phi is basically the first basis function and the second basis function when you put the first sample in there. Okay, I'll say that one more time. The first basis function and the second basis function. So the first basis function, what's that? Xi. So if you put it means that if you put some number in there, it just give you that number back. So if you put the first sample in, it just give you the first sample back. And the second one always gives you a 1, so it's always a 1. You put the second sample in, it gives the second sample back. So this matrix, how do we obtain them in a one-dimensional situation? Is you simply copy the samples here, right? You just copy all the samples here, and then you put 1 for this entire column, and that's it. That is how you get phi. So let's do a quick example. Let's say we have the label. These are the labels. So if you have x1, you want functions that predict y1 is equal to 1. If you have x2, you want a function that predict y2 is also equal to 1. So these are the functions. Now, how do you get phi? Well, I just told you. You basically copy this. And the reason you copy this is basically from here. And then for the second column, you just put ones. So this is it. For linear regression, you simply need to take the data, convert it into this giant phi matrix, right? The feature map of every single sample. Once you have this phi, your optimal solution is W. Yeah. Now, in order for like it's very easy for you to just copy this and basically use it to solve in the future. However, it doesn't mean you understand what's happening. In order for you to understand, you really would need to understand how this phi came about, and this is what like this lecture we've been talking about. Okay, so so um, I think this, yeah. So this was the problem we solved last time. Okay, so given a simple closed form solution, all right, if you have this data, then the phi matrix becomes this, right? Because well, you just copy this and you put one here, and then after that, these are the labels. This is why, right? This is all the labels. So after you solve the closed form solution, right? Use NumPy. Now you want to pause to essentially calculate W, and you should get this solution. You want to compare this with your gradient descent. So if you solve a gradient descent, you should also have this. When you solve a closed form solution, you should also have this. Okay. So the closed form solution is so much easier to calculate. You generate this and you just multiply them together, and you got the solution. Gradient descent is more complicated. However, it works for anything. All right. Even when the closed form solutions doesn't exist. Okay. So after that, uh, for the students who finish this, right? So what I want you to do is, if you haven't finished the gradient descent, you want to continue with the gradient descent. You want to make sure you get that, and then you want to make sure you can get this as well. If you can finish that in time, then you want to try the second one, which is for the polynomial regression. Now with polynomial, right? The what were the feature maps? Is different, right? So if you have linear regression, xi, and you put it into phi, the feature map, your result is xi1, right? So that's with linear. Now with polynomial, second order, then you put xi in, your result feature map would be xi squared and then xi and 1. Okay? So so this is for one sample. If you have multiple samples, like n sample, then be x1 1, x2 1, x3 1, so on and so forth. Over here would be x1 square, x1 1, x2 square, x2 1, x3 square, x3 1, so on and so forth. So the feature map, this phi matrix, would be different depending on the basis that you use. Okay. So I wrote the code here. This is for the closed form solution. Closed form. You wanna don't look at my code unless you're really desperate. But give it a try. Try to write it yourself first. And if you really don't get it, you can take a look. Notice how it's impossible for you to draw a parabola that will hit every single point, right? So you can only draw the parabola that fits this the best possible. You will have some error. Your error is not going to be zero, right? So so yeah. Yeah, so this is your first exercise. I hope you can finish. Now let's move on to multivariate. We just talked about single variate, which means that you have x and you have y, right? You're trying to take x1, x2, and you're trying to predict y1, y2. So you have a function, you put x1. Ideally, you get it approximately to y1. Like that's the goal. But when you have multivariate, right? No, that's different. It's no longer just one, no longer just one input. So what you have is you end up having multiple inputs. Let's see, how should I represent multiple inputs? I don't really like the notation here I have because it's a bit confusing. Let's say we have multiple inputs and we're going to call the inputs. What are we going to call the inputs? We're going to call the inputs y. No, that doesn't make sense either. X hat, I guess. I guess. No, that's also not good. All right, 1 second. You've Okay, well, this is what's going to happen. We're going to call the inputs x1 as the first input, x2 as the second input. Notice the bracket. And therefore, if we have x1, which is the first sample, x2 is the second sample, then x1, 1, that will be the first feature of the sample. Okay, so my point is, let's say previously you have X and you're trying to predict Y. But now what you have is X1, X2, X3, so on and so forth. And given multiple factors, you are trying to predict Y. So this is why we call a multivariate regression. For linear regression, it's pretty simple, right? For linear regression, what if you remember, if when there was only one variable, x and y, in the end, it's just w times x plus 1. And ideally, that equals to y. But when you have multiple of them for linear regression, it would be just w1, x1 plus w2, x2 plus w3, x3 plus 1. So depending on how many dimensions, how many inputs you have, it will essentially be, it would be the dimensions times weight. So it's a linear combination. It's a linear combination of the features you have plus 1. Okay. So this right here is your feature map. So when you're trying to do a feature map from xi, it will become x1, sorry, x1, x2, x3, and then 1. And all these are sample 1. And now you have second sample, first feature, second sample, second feature, second feature, third, and 1, and so on and so forth. This is your 5 matrix. So when you're calculating the the regression, and you also need a 5 matrix, this is how you do it. Okay, so that's for multivariate. So one thing I want you to notice, once you have the 5 matrix, the solution is the same. The solution is still phi transpose phi inverse phi transpose y, right? The size of these might change, right? But the equation doesn't. Okay? Now, that was for linear. That was for linear. When it's linear, what's happening is you, for each dimension, you just add a weight to it. For polynomial, it's much, much harder. So the feature maps of polynomial, let's say you have 3 dimensions, 1, 2, 3. 3 dimensions. If you have 3 dimensionals, then the polynomial would be like x1 square, x2 square, x3 square, 1, x1, x2, x2, x3, x1, s. Basically, every combination will have to be taken into account. Now, doing this is very, very tedious. So I don't expect you to do this. However, I do need you to understand that the concept of mapping the data x1, x2, well, I should have written x1, x2, x3 into the feature maps. Okay. Now, for polynomial, it is much easier to generate this phi matrix with just the feature map. Now, on the exam, coding exam, you can just use this. For the written exam, I'm going to make sure I give you a really easy one so you know how to do it by hand. So what it does here is this, by calling this function, you create a polynomial feature map and you can transform your entire data set. So this data set is, this data set is 5x. Actually, I should have written that. This makes life a lot easier. So over here, I have written the code that essentially does this one here, I think. Right? I think that's what it does. So, this is the code actually. Nope, this is the code. This is the code for your practice, in-class practice. So over here is the polynomial. Okay, over here is the polynomial. You have to make sure you include the library, and you can make prediction of stocks. Okay, so in-class work. For the in-class work today, your goal is to load these files. Okay, so this is basically a bunch of data you collect. Once we collect this data. This is the stock price for the next day, a differential. Like, did it go up by this much? Did it go down this much? So your goal is to take this data and see if you can predict the stock price. See if you can run the linear regression, because that's the easier one. Hopefully you can do that. And you want to use gradient descent to solve it. What I want you to do is, when you do gradient descent, I want you to plot the error, between the difference between your prediction and the truth. So this error should be going down, right? Ideally, as you run gradient descent, as you increment through gradient descent, your error should be going down. So you want to plot that out, and then later on confirm your result using closed form solution. Okay, and then you can calculate the final error that you have. Once that happens, what you can do is you can print your predictions. So y hat, these are your predictions. So you say the stock went up by $1, and the truth is you went up by $1.20. And then that's for sample one. For sample two, maybe it went up by $2, but your prediction is $1.25. Maybe the third one is went down by $1, but your prediction was minus 0.5. So you want to print this out to see how good a job you predicted. For those of you that can finish, you also want to, ahead of time, you want to do the second order polynomial as well. So this is the class exercise. Originally, I had prepared this class to be much, much bigger. Remember to submit your classwork. It's actually, there's a lot more stuff I originally was going to talk about, but I've decided to skip them, given how some of the students are feeling basically really stressed out, and I need to slow it down a little bit for them. But for those of you that wants to go along, you want to go over these slides and see if you can understand them. This, I'm not going to expect you to know this on exams, but for those of you interested in learning more, you want to go through these. Okay, so that's it for today. I will see you in the next class.